Let us start our study of Deuteron. Now you see, this nucleus Deuteron, simplest two-body system which exists, is unique in many ways. Number one, what do you think? It is only loosely bound. Very loosely bound. Its average binding energy is very much lesser than your 8 MeV. That is the average value between pair of nuclei for all stable nuclei. Okay. How much is this? Do you know the average binding energy of Deuteron? You must remember this. The average, it is approximately 2.225 MeV. This is the binding energy of Deuteron. Now, this observation we use nuclear reaction to get this estimate. Okay. Now, mainly because of this small binding energy, the Deuteron has no excited state. So, basically due to this small binding energy, second unique feature, no excited state. And so, all observations on Deuteron are made on the ground state. Abar ki holo? These are some very basic information on Deuteron. I have just given you the binding energy now and information which is 2.225 MeV. Next I told you no excited state, and so all observations of Deuteron on ground state are made. So just let me write down some of these ground state properties. Okay. Just let me write it down. Say for example, the spin parity of ground state, this is 1 plus. So these are all ground state properties. Next, the total isospin is 0. Okay. Next, the magnetic dipole moment, its value is 0.857. I'm just writing up to 3 decimal places. Next, electric quadrupole moment, QD, this is 0.286. And finally, the radius of Deuteron, which is 1.963 Fermi-meter. I have not written the uncertainties, I have just written the without uncertainties. These values I have just written over here. They are the ground state properties, and we are going to exploit these properties and we are going to talk about them in our class. Now, so the first thing that I am going to talk about is the parity. Okay, so first let me talk about parity. Now you see, the parity of a state describes the behavior of its wave function under the reflection of the coordinate system through the origin. This I am again not going to talk about in detail. This you have learned in your previous classes. Now for the Deuteron, it is known that I have already showed you the data that the parity of the ground state wave function is positive. Parity is positive for ground state wave function. Right? Now let us see what we can learn from this information. So info 1, this will be our first information, this thing, that is the parity is positive. You must be wondering, what is this happening? Such a trivial thing, parity is positive. What can this positive value tell us? You must be wondering. So just continue listening to me. Now, to start with, let us separate the wave function into 3 parts. So the first thing, let me write down the wave function into product of 3 terms, 3 part separation. So what are the parts? Number one is the intrinsic wave function. Intrinsic wave function of proton. What is a deuteron? Basically system of proton and neutron, right? So the first is intrinsic wave function of proton. Of course, the next is intrinsic wave function of neutron. And what next? Relative concept. So the next is the orbital wave function. Orbital wave function. And what does this describe? Orbital wave function for the relative motion between the proton and neutron. Right. Now you see, since the proton and neutron, what? They are just 2 states of a nucleon, so their intrinsic wave function have the same parity. If they have the same parity, whether plus plus or minus minus, the multiplication will give you positive value. So overall, from their product you will get a positive result. So as a result, the product of the intrinsic wave functions has positive parity regardless of the parity of the nucleon. Fine. So this means this overall wave function, its parity will be decided by this factor. So this is the factor which will be playing the role for parity, the orbital wave function. Now let us continue. Now you see, for states with a given orbital angular momentum L, the angular dependence of the wave function what does it? So how do we get this? It is basically given by this YLM theta phi. That is the spherical harmonics of order L. Now, under an inversion of the coordinate system, these spherical harmonics, they also transform. Okay, so that as a result of this transformation, we get YLM pi minus theta and pi plus phi, and the result is this minus 1 to the power L into YLM theta phi. So basically this means that the parity of YLM is minus 1 to the power L. Okay. Now the fact that the parity of the deuteron is known to be positive, what does this mean? This means that this L must be even, right, since this is positive. Okay, any questions till now? Koto golpo. So what is the result of all this basic investigation? Information 1 was ground state has positive parity, and overall what is the result of our investigation? We now know that because the ground state is positive parity, so the L must be even. This is info 1, right? So previously this was experimental info 1. This is our experimental info 1, and this is now what we are getting is the observational info 1. Now we have talked about parity in info 1. Now we will talk about info 2, and this time we will be talking about spin. Previously we talked about parity. Okay, now you see the spin of the ground state of Deuteron. Spin for ground state is what? J equal to 1. Now, so spin of ground state of Deuteron is J equal to 1. Now we already know that J is equal to L plus S. Good. So the possible values of S, the sum of the intrinsic spins of the two nucleons, are 0 and 1. Now we can just eliminate this 0. We can eliminate this. Can you tell me why? This we will eliminate. It cannot be equal to 0. Since it is not possible to couple S equal to 0 with any allowed L value. Remember, what is this? This is even. L is even. We just got the information info 1 on parity. We got this information, right? That L is even. And so possible S values, so that we can have J equal to 1 is 0 and 1, but S equal to 0 coupled with any even value will never give us J equal to 1. So this is not possible. Fine. Also we can rule out any L greater than 2 by the same argument. So two things. One, L is even. Another is L is not greater than 2. So these two things are not possible. That is, S equal to 0 and L is greater than 2. This is not possible, because only with L equal to 2 and S is equal to 1 we can have J is equal to 1. Okay. Thus, if we consider information 1 and information 2, that is J pi equal to 1 plus, then we can have only possibility for LS as either 0 1 and 2 1. These are the possibilities. Now we will later see that the dominant part of the ground state wave function has this L equal to 0 component with a very small but significant amount of mixture of this L equal to 2 component. Okay, let us, before proceeding, just recap what we have done. So we have basically talked about the ground state properties of Deuteron, right? So now you see, we have first talked about this positive parity information on the ground state wave function. Okay, so what information can we obtain from the positive parity? Basically the fact that L must be even. This was the information obtained from parity. Okay, so this information was obtained from parity. Next we consider the spin of the Deuteron. Then after considering the spin of the Deuteron, we observe that from the spin we can get this information about the LS possibility. What can be the L and S for the ground state of the Deuteron? So there are two possibilities, either this or this, and this information was obtained from the spin. Okay, and now third part that we will be continuing today. So the third part is regarding the Deuteron isospin, and here we observe that there are two possible candidates for isospin. It can be either t equal to 1 or it can be either t equal to 0 isospin, but we are not that much sure about it. Which one will it be? Okay, so let us consider the following set of arguments. Okay, let us consider to confirm which one will it be, whether it will be t is equal to 1 or t equal to 0. To confirm this, let us consider the following set of arguments. Good. So let us consider that the ground state of the Deuteron is, let us consider ground state of Deuteron is basically t equal to 1, right? Now what is Deuteron? Deuteron is basically NP system. Now similar, we have two neutron system, NN and PP. Okay, good. Now yes, now if the ground state of the Deuteron would be having t equal to 1, then similar bound states will also exist in the other t equal to 1 two nucleon systems. So all these three are t equal to 1 subsystems. All three of them will have that. However, we already discussed about this, remember? However, no such bound states have been observed for this di-neutron and di-proton. Now we were also considering the fact that di-proton cannot exist because of the Coulomb repulsion between the two protons, and it is very simple that if you consider the distance of the order of 1 Fermi meter, then the Coulomb interaction, okay, between these two protons, you will find that the Coulomb repulsion is of the order of 1 MeV, and we already know that the binding energy of NP system is of the order of 2.22 MeV. So since these are quite close, so you might say that, okay, since the Coulomb interaction repulsion between the two protons is of the order of 1 MeV, so we can say that proton-proton is justified for being not bound. But we will see that this is partly a reason. There is another reason as well. Anyway, now since this value is a large fraction, as I was saying, you see this 1 MeV is a large fraction of this 2.22 MeV. So it is difficult to expect that a bound state can happen for this PP system. di-proton system. However, there is no such scenario for NN system. So why does it not exist? The fact that the new di-neutron system doesn't exist, which will be having T equal to 1. Okay, remember what is the total T0 for diproton? This is plus 1. Total T0 for di-neutron, this is equal to minus 1, and for NP system this is equal to 0. Okay, now this one we have confirmed that it does not exist because the Coulomb repulsion is a large fraction of the binding energy. However, this one does not exist. This means that there is something wrong with our proposition itself, that is T equal to 1. So you can say that since no bound state is observed, so let me write it down. Since no bound state is observed for 2 neutron, so we conclude that it is not possible to have T equal to 1 bound state for, just a second, for 2 nucleon. Okay, so this means that the neutron proton system will have T equal to 0 for the ground state. Any questions? So this is basically yet another information that we have obtained. Okay, so this is info 3, isospin, this one, T equal to 0. Continue. Okay, so let us now summarize what we have done. So basically what we have done, we have considered the parity, then spin, and then the isospin for ground state of Deuteron, and we have observed or basically obtained certain information. First one, this give me that L should be even. Next, what does spin give me? Yes. So where is it? Yeah. So the LS values can be either 0, 1 or 2, 1. And isospin, it told me that we must have T equal to 0 for the ground state. So these are the 3 information that we obtained. Okay. See here, interestingly, although T equal to 0 and in both these cases S is equal to 1. However, there are 2 possibilities for L. 2L. See here, we can have L equal to 0 and also L equal to 2. Now, in spectroscopic notation, we say this L equal to 0 and S equal to 1 state as triplet S state. Whereas the other one, which is L equal to 2 and S equal to 1, we call this triplet D state. So let me use different color. Okay, where is it? Yes. So this we denote as 3s1, and this we denote as 3d1. See? Now, again, another very interesting argument. Okay. You see, if n, L and S are both good quantum numbers, so let me write it down. If L and S are good quantum numbers, that is, so this means if the nuclear Hamiltonian H, it commutes with L square and S square, then the ground state of Deuteron would have either of these states. Okay, that is what? Okay, so either of these two states means this 3s1 or 3d1. Fine. Good. Now, you see, there is no reason to believe that this shall not be true. And in fact, there are evidence which shows that both these components, this 3s1 and 3d1 components, are present in the Deuteron ground state. Okay, and this leads to the conclusion that, what does this mean? So, conclusion, is that the nuclear force mixes different L components in an eigenstate. That is, what does this mean? This means this H L square commutator, this is not equal to 0. Okay. And this information that the component is present in both Deuteron ground state, this we will get the evidence while analyzing the electric quadrupole moment and magnetic dipole moment. This information, component present in the ground state Deuteron, this is obtained from electric quadrupole moment and magnetic dipole moment analysis when we do that. Fine. So you see, this is a very important information that we have obtained. And this is your info 4 regarding the nuclear Hamiltonian H. This very fact that Hamiltonian H doesn't commute with L square. Okay. So these are the info 1, info 2, info 3. So this was, where is it? Oh. This is info 1, this was info 2, then this was info 3, and now we have this info 4, that is nuclear force mixes different L components in an eigenstate. Fine. So we have considered and obtained 4 very useful information for the ground state of deuteron. Now, what about this state j pi equal to 0 plus? What if for the deuteron we observe this j pi equal to 0 plus? In fact, this is observed for the first excited state for deuteron. This is observed. So this is an unstable state, of course. First excited state for deuteron, we observe the spin parity to be 0 plus. Now j pi equal to 0 plus, this means that L equal to 0 and S equal to 0. Okay. Now let me write down the wave function. এই তোমাদের বোঝা যাচ্ছে? কেউ কিছু বলছো না, চুপ করে বসে আছো?
হ্যাঁ স্যার।
ঠিক আছে, এটা বেসিক জিনিস, একদম বেসিক জিনিস। What I am saying is, you see here, see the spatial wave function, we have already discussed about this. L equal to 0, so this is positive. And what does this mean? This is your symmetric under permutation. So this is symmetric under permutation. Again, this one, the spin wave function, this we have found anti-symmetric under permutation. Now the total wave function must be anti-symmetric, and this one is anti-symmetric, this one is symmetric. So what about this isospin? It has to be symmetric. Otherwise the whole wave function, it cannot be anti-symmetric, right? So this means that if isospin has to be symmetric, then there is only this possibility, t is equal to 1. See? So this means that if j pi equal to 0, which is observed for the first excited state of deuteron, then it will have t is equal to 1, and this will also be valid for both NN and PP systems, di-neutron and di-proton systems. Okay, so we can say that if the nuclear force has been such that both di-neutron and di-proton exist, then the ground state would be having j pi equal to 0 plus and not. So basically, if both NN and PP would have existed, then the ground state of NP, NN, PP all will have this j pi equal to 0. Understand? So this is what we have observed from our very basic analysis by breaking the total wave function into 3 components: spatial component, spin component and isospin component, and then considering the symmetric or anti-symmetric behavior of each of them under permutation. Fine. Just a second. So any questions till now? What we have considered? So basically we are considering a different argument for finding the ground state isospin of deuteron, right? So we have already considered the fact that both proton and neutron are two different isospin states of nucleon, and so they can be considered as identical particles. So the total wave function of the system must be antisymmetric under the permutation of indices of the two particles. So we can write like that, and as a result we have written the total wave function in this fashion. You see, we have decomposed into spatial component, spin component and isospin component. Then we have done the analysis for spatial component. So basically permutation in R, if we consider spherical polar coordinates, this corresponds to this transformation, and since both L equal to 0 and L equal to 2, so in both these cases this will be governed by the spherical harmonics, where minus 1 to the power L will be the only change that we have considered, and it will be symmetric. So the spatial component will be symmetric. Next we have considered the S is equal to 1 scenario, and we have written down S is equal to 1. There are three possibilities of MS. We have considered the wave function for MS equal to +1. We have written over here, right? And you see there is hardly any change if we change the indices. So this means there is symmetric, and the other two S is equal to 1 states having MS is equal to 0 and 1, they can be generated from this wave function itself. So overall the spin component is symmetric. So this means that here the spatial component and spin component are both symmetric. So this means the total wave function can be antisymmetric only if the isospin is antisymmetric. Fine. So this is what I am doing. So I am writing down the t is equal to 1 state, and the t is equal to 1 wave function will be very much similar to this case. What about the t is equal to 0 component? This is what I want to write. And remember, t is equal to 1 state is very much similar to this spin state. Then if it is very much similar, then the t is equal to this 1, it will be again symmetric like the scenario over here. And remember, we want the isospin to be antisymmetric. So which one can be antisymmetric? The t is equal to 0. So right now I am writing down the wave function for this t is equal to 0 state, right? So this is what I am doing in case you are getting confused. So I have recapped. Fine. So t0 equal to minus half indices 1, write this. Okay. So this wave function describes the t is equal to 0 state. Now you can see that the right hand side of this, here you can see what will happen if we apply the isospin raising or lowering operator. Then the RHS here, the entire RHS, this entire two terms, they will just vanish, and the requirement that the isospin part of the two nucleon system is antisymmetric, then what does this imply? This implies that the ground state of the Deuteron has basically t is equal to 0. এই বোঝা গেছে? এটা হচ্ছে সেকেন্ড আর্গুমেন্ট, আমি দুভাবে তোমাদের দেখালাম. So I have showed you why the Deuteron ground state will be t is equal to 0 state. I have used two different arguments. First, I have considered that the ground state is t equal to 1 over here. Where? Just a second. Yes, the ground state, if it is t equal to 1, then we have observed that Nn and Pp don't exist. We have talked about it. So this means that t is equal to 1 does not exist in the ground state. However, the excited state can have t is equal to 1. See here, and we have talked about this in details over here. So any more questions? Okay, So after our